Okay, good evening to our colleagues in India, and welcome to everyone here in the US. I'd like to thank you for joining us today to our 12th seminar in the joint webinar series between Binghamton University and Vellore Institute of Technology. This is our last seminar in 2020, so we will rejoin again in 2021 with more exciting presentations from researchers and faculty from both Binghamton University and Vellore Institute of Technology. So today we are delighted to have Dr. Niroj Kumar Sahu, who's a professor, associate professor in the Center for Nanotechnology Research at Vellore Institute of Technology, India. Dr. Niroj Kumar Sahu has received his MTech degree from NIT Rourkela and Ph.D. degree from IIT Bombay, India. He is currently an associate professor, again, as I said, in the Center for Nanotechnology Research. He has authored or co-authored 29 journal articles, 6 book chapters, 3 review papers, and 7 conference papers. His current research interests include magnetism and magnetic materials, specifically ferrites based nanostructured magnetic materials for hyperthermia, thermochemotherapy, and MRI applications. So Dr. Niroj Kumar Sahu, thank you very much for joining us. We are delighted to have you. And on behalf of Binghamton University and VIT, welcome to our webinar series, and I will turn it over to you for the presentation.
Yeah. Thank you, Mohammed, for a brief and nice introduction. And a very good morning to all my friends or participants from USA and all my colleagues and participants from India. Today I'm going to speak about a little bit about my research area regarding the my research area is basically based on the extensive study of the materials, and we are doing some of the bio applications of especially magnetic materials. Okay, am I audible?
Yes, sir.
Yeah. Yes. So the outline of my presentation is as it is biomedical application. I'll tell a little bit about cancer and cancer statistics, then cancer therapeutic techniques and hyperthermia, then magnetic nanomaterials and heat generation mechanism, processing of ferrite nanomaterials, functionalization strategy and their properties, application, especially what we have done, that one I will present, that is in vitro cancer therapeutic results, and then acknowledgement. All right. So what is cancer? Cancer is an unregulated cell growth, and it has a complex tissue structures, and there is cell destruction or DNA gets damaged from its proper functioning, causing a cell mutation. So there is it behaves completely different from the normal cells, and after sometimes it invades the surrounding healthy tissues. All right. So if you see the cancer statistics or cancer facts and figures from American Cancer Society, the estimated new cases in cancer in American peoples are the breast cancer, and around 0.3 million estimated new cases has been predicted in the 2019, and the estimated deaths are around 42,000, 42 around 42,000. And among these, the most leading cancer is generally lungs and lung cancer and breast cancer. Of course, there is colon cancers are there, and other cancers are also included. But the breast cancers is the most leading cancers among the women. All right. So if you see the cancer global impact and the death due to the different diseases, the leading diseases among the people is due to cardiovascular diseases, and followed by the cancers, and then you have respiratory diseases. Of course, this is the coronavirus, and all of you are aware about the COVID-19. So cancer is one of the most dangerous disease which affects the the globe in a substantial way. So you will see the statistics around 8.2 million people die from cancer worldwide every year. And new cancer cases are expected to rise to 70% within next 2 decades. And over 100 cancer type exist and each requires unique diagnostics and treatments. So it's not a the cancer is not that one or two types or few types, but rather there are hundreds types of cancers are there, and it needs every cancer needs unique techniques or unique diagnosis techniques and treatments. And if you see the cancer burden in 2018, the socio-economic inequalities a major cause for rapid rise in cancer cases in India. And there are estimated 1.16 million new cases in India, and zero point 0.7 million deaths are there. And as I mentioned, the breast cancer is the number of cases. Six most common type of cancers are breast cancer, oral cancer, cervical cancer, lung cancer, stomach cancer, and colorectal cancer. So you can see in men, there is oral, lung, and stomach are accounted for around 45% of new cancer cases. But in women, generally breast and cervical cancer and ovarian cancer are cancer account for around 60% of the cases. All right. So you will see the type of cancer and therapies. The type of there are two type of cancers. So one is benign cancer and another is malignant cancer. So in the benign cancer, the tumor cell grow only locally and cannot spread by the invasion or metastasis. So the cancer, one of the dangerous thing is that it starts from the own body cells. It doesn't come from the outside like any virus or bacteria. Rather it start from own body cells, and there is not a particular reason why the cancer is happening. There are many reasons are there, and the lack of immunity is the pollutions, the improper food habits. uh, People are using pesticide insecticides in the vegetables. Many things are there, and then alcohol consumptions. So all these things, but there is no specific reason why it is happening, because it starts from the normal cells only. So benign cancer stay at one point, but however, malignant cancer cell invades neighboring tissue after a certain time, and enter the blood vessels and metastasizes to different sites. All right, and it is very dangerous if it cannot be diagnosed in the preliminary stage. It is the cure rate is very less. So if you see the different type of therapeutic techniques available for the cancer treatments, generally surgery is there, which is invasive techniques. Then chemotherapy, administration of drugs. There are different drugs are there, and as I mentioned, there are different type of cancers are there, and it needs a specific type of treatment. And then there is radiation therapy, which is this chemotherapy and radiation therapy are usually practiced by the most commonly practiced by the doctors. And in radiation therapy, high energy radiations of X-ray, gamma ray, or charged particles are being put to the body, and the cancer cell has been irradiated with the high radiation, and there is cell death mechanism is there. And there is immunotherapy, and in the immunotherapy, using substances made from your own body. So it started from the own body or in a laboratory, and then you have to then the immune system of the body has to be increased to kill the cancer cell. Of course, there is gene therapy is also there, using gene by replacing a mutated gene that cause disease with a healthy copy. So those cancer cell, which is generally the operated by or controlled by the gene, that mutated gene is being replaced by a healthy copy, or inactivating or knocking out a mutated gene that is functioning improperly or introducing a new gene into the body. So if you see the major drawbacks, the major drawbacks are unavoidable effect on normal healthy cells. So if you see the chemotherapy, after certain doses of chemo, it's gradually, all the body is getting contaminated, and it's creating a lot of problem to the or inconvenience to the body. So if you see this type of therapies, there are unavoidable effect on normal healthy cells, and hence these treatments have their own limitations. So if that is why people are going for the research to have the better treatment or better therapeutic techniques, and in the front line, nanomaterials are being used for, of course it is not in the clinical stages, but researches are still going on nanomaterials to see the better therapeutic techniques in future. So why nanomaterials are very important is that nanomaterials length scale match tumor endothelial junctions, resulting in effective penetration and retention for localized applications. So if you see the nanomaterials, so we'll see the length scale of the nanomaterial. The atoms are around zero point 0.1 nanometer, and you will see DNA, protein in nanometers are around 10 to 100 nanometers. Not exactly the same dimension, but generally less than 100 nanometer. And if you see the virus and bacteria and human cells, or the cancer cells, these are in the micrometer range. So it can easily penetrate. Of course, there are different techniques, functionalization techniques, to get the effective penetration and retention. So the nanomaterials have the advantage of different functionalization and attachment of other drug molecules or medicines, so that it can go and do the job inside the cells easily. So there are nanomaterials like magnetic nanomaterials. It is it can be attached to the targeting agents. It can be coated with the different biomolecules or organic molecules, and then chemotherapy can be also attached, so that it will go and directly bind to the cancer cell, and it will do the targeting or MRI diagnosis, and that is drug delivery is there. And hyperthermia, what is hyperthermia or heat generation, I'll tell you in the next few slides. All right, hyperthermia is one is the cancer treatment is through the chemotherapy, and their drug is being administered and drug is doing its job. However, in radiation therapy, the high energetic radiations are being embedded, irradiated on this tissue, and tissue structure has been destroyed. However, in the hyperthermia, there is the heating response. If you heat this is a tumor cells, and if you heat the tumor cells through certain mechanism, some of these tumor cells are very susceptible to heat, so they cannot function as the cancer cells should function, and there is necrosis or apoptosis happens. It is generally necrosis because uh, triggered cell deaths are there, and it destroy the cancer cells. So hyperthermia is nothing but you have to apply the heat and to these tumor cells, and there is heat shock response, and the apoptosis happens. So what will happen is there are certain the hyperthermia is generally operated at around the temperature of above 43 degrees centigrades, and at the nearby the temperatures the normal healthy cells can withstand the temperatures by producing certain proteins. But in the cancer cell, it has been found that if you increase the temperature above 43 to 45 degrees centigrades, then it undergoes necrosis and there is cell death occurs. All right. So is tumor physiology susceptibility to hyperthermia? Yes. So tumor have heterogeneous tissue structures and is display the chaotic vascularity, high interstitial fluid pressures. There is high interstitial fluid pressures are there, and significant deposits of dense and fibrous stroma are there, and regions chronically deprived of oxygen. Generally, it is called the hypoxia. So and there are many therapies. One is starvation therapies are people are doing. So the glucose, the cancer cell consume more glucose than the normal cell. So if the glucose has to be the supply of glucose has to be stopped, or the glucose the form of the glucose will be changed by some of the using some nanoparticles, then the glucose supply can be limited, and there is the cancer cell death of cancer cell. Or some people are doing the the reactive oxygen species treatment, and as it is the cancer cells survive generally in hypoxia conditions, so there is less oxygen is there, deprived of oxygen. So it will oxidize, it will supply the oxygens through uh, the reactive oxygen species, or oxidize these systems, then also it is getting that. So in hyperthermia, if you apply the heat, then there will be the denaturation of the intercellular proteins or disruptions of cellular membrane, and this happen because the ruptures of the cellular membrane happens because there is increasing in blood perfusions. So there is uh, increasing in blood perfusion, and it modify the tissue structures. And if you see the cancer therapy also, some of the cancers are they're not responding to the particular drug, and because of that the doctor are practicing like they're giving the radiation first and then going for the chemotherapy. So there is the combination therapy, or it is generally termed as the synergistic therapy too. All right. What are the different type of hyperthermia based on temperature? There are different temperature regions. One is called the thermoablation if the temperature is greater than 45 degree, and if directly the 40 you increase the temperature to above 45 degree, then there is necrosis happen, means it cell death occurs. But however, if the temperature has been will be increased to 41 to 45 degree in a controlled manner, then there is control cell death happens. And the moderate hypothermia is generally being adopted for the treatment of cancer because it doesn't have much adverse effect to the healthy cells. All right, and there is diathermia. Diathermia is generally less than 41 degrees centigrade, and we are generally treatment of rheumatic diseases in physiotherapy. Generally, heat treatment are being given to treat some rheumatic diseases. All right. So based on the extent of area or location and depth, different type of cancer therapy can be administered. And what are the parameters to be focused during the treatment is amount of heat generated, exposure time, type of cancer cells. So the major challenges is selective heat delivery sparing the normal healthy cells. So if we increase the temperature of a particular cell at directly above 45 degrees centigrade, then healthy cells also cannot survive generally. So to have the control heating abilities, magnetic nanoparticles are being administer. Magnetic nanoparticles are being of uh, it is of research because this can generate the heat in a very controlled manner. So there are many hyperthermia techniques are there, but they have their own limitations. And some of the direct energy devices like ultrasound, radio frequency, microwave, infrared radiations can be given for heat generation. However, these have limitation like unavoidable heating of healthy tissues, limited penetration of heat into the body tissues, insufficient tissue or specific control. We cannot control it because the heat can directly transfer to the cells, and it can kill the healthy cells. And the doses in the target region, in the case of bone or pelvis or skull, cannot be control in a proper way. Yeah. So these techniques, the infrared or the laser or ultrasound, if this has the limitation, then how the magnetic nanoparticle can be tuned? So how heat can be generated? And this is generally called the nano heat generator because nanoparticles are being used. And how magnetic nanoparticles are being used? The magnetic nanoparticles, the magnetic properties is being utilized for the generation of heat. So there are different mechanisms for the heat generations. One is hysteresis loss for magnetic materials. It will see the magnetic materials. It shows the in the bulk form or at a particular nanometer size. It shows the ferromagnetism, and if it goes to a below certain value, then it shows the superparamagnetism. Of course, there is Neal mechanism and Brownian mechanism are there. Neal mechanism is based on the relaxation of the magnetic moments. When you apply the field and switch off the field, then the magnetic moment will get relaxed, and it will generate the power or heat. And there is Brownian mechanism because the nanoparticles will be in the colloidal suspensions, and during the movement of the nanoparticles, the physical moments of the nanoparticles will give you the Brownian mechanism. So these happen in the superparamagnetic materials, and we can see that this is the coercivity and the crystallite size of the materials. And if you decrease the crystallite size of the materials, the multi initially in the bulk it is multi-domain region. When you decrease the size to a particular size, the still it is in the multi-domain region, but the coercivity is quite high. So coercivity, when we have the coercivity, it looks like this, means it will develop the permanent dipoles. And as we are applying the AC magnetic field for, we are employing the AC magnetic field for the generation of heat, because we have to go for the several cycles. We don't need ferromagnetic materials, because as it develops the permanent dipole moment, and there will be these magnetic particles will stick together due to the development of the dipole moments, and there will be cluster formation, and which can create a lot of problem in the body. However, we want the heat generation mechanism. However, the when we switch off the field, there should not be any development of permanent magnetic moment, and it should this is apply the field, you will get the magnetization. When you nullify the field, you will get the zero magnetization, means it will act like a simple particles. It's when you nullify the field. When you apply the field in this direction, it will get situation again. When nullify the field or switch off the field, then it will come to the normal position. So no permanent dipole will be dipole moment or permanent magnetic moment will be developed in the materials. So if we see this coercivity for versus crystallite size, then if we decrease the crystallite size, this is the multi-domain region, and here it comes to the single domain region, and still it possesses the coercivity. See, coercivity is maximum, and of course in this size generally it is used for the magnetic energy storage devices. However, if you decrease the size of the particles, the coercivity get decreases, and at a particular size, the coercivity is zero. And when the coercivity is zero, we are getting the super paramagnetic nature. All right. So the critical diameter where the coercivity is zero, it depends on the several factor. And the several factors are, one of the major factor is the saturation magnetization and effective anisotropic constant. So the effective anisotropic constant is due to the shape of the magnetic materials and due to the crystal orientations or the magnetocrystalline anisotropy of the material. So that has to be, and as the magnetic saturation and anisotropic constants are different for the different type of materials, and hence the critical diameter is also different for different type of materials. So generally, if you take any ferromagnetic or ferrimagnetic material like iron oxide, here we are using the iron oxide has a specific size, and below around 80 nanometer, it is showing the superparamagnetic region. And superparamagnetic is required, and the heat will be generated through the Neal mechanism or Brownian mechanism. So the Neal relaxation, as I told, that you apply the field, the magnetic dipole will orient along the direction of the field. But when you switch off the field, it will come to the original positions, and hence it will release the energy, and the release energy will be converted, or it can be in the form of heat, and there will be power dissipated. And in the Brownian relaxations, there is the actual movement of the particles. So we are applying the field in both sides with the high frequencies. So we are changing the dipole as well as, we are changing the north pole and south pole of the applied magnetic field. I'll show you in the instrument how we are doing. And because of that, there is colloidal movement, and colloidal movement also generate the relaxation that is called the Brownian relaxation. So this is due to physical rotation of the particles, and this is due to the spin rotation of the particles. And we see that the Neal relaxation due to the moment developed, it depends on the several factors. So these several factors are generally Kv is the anisotropic constant, and V is the volume of the particles. And the Brownian relaxation depends on the eta, the viscosity of the fluid, and the hydrodynamic size of the particles. And there is effective anisotropy, and effective anisotropy is 1 divided by, in effective anisotropy is 1 divided by tau b plus 1 divided by tau n. And if you do this, effective anisotropy can be written as tau b tau n divided by tau b plus tau n. All right. So the power dissipated in these nanomaterials due to this relaxation mechanism is depend on the various factors. The power dissipated is ms, the saturation magnetization, the volume of the particles, the frequency at which you are applying the field, and what is the strength of the field. So this depend on particularly this factor as well as the effective anisotropy factors. So these effective anisotropy factors, so the effective relaxation factor depends on the susceptibility of the materials too. So this depend on the susceptibility. The effective relaxation depend on the magnetic susceptibility of the materials. Susceptibility means the susceptibility is generally termed as the magnetization versus the applied field. So if you apply small field and you are getting higher magnetization, the susceptibility will be higher. And if you are applying to get the magnetization, you have to apply a high field, then the susceptibility will be low. So we want the higher susceptible materials to increase the effective anisotropy, and to increase this factor, not effective anisotropy. This factor is a complex factor, and which depend on the complex part of the susceptibility of the material. So the specific absorption rate, so this is the power dissipated due to, and as I reiterate that it depends on the saturation magnetizations, it depends on the frequency of the applied field, it depends on the strength of the applied field, and it depends on the susceptibility of the materials, which finally decides what is the effective relaxation times. So based on this, the specific absorption rate, or this is called ACR values, is equal to the specific heat of this liquid, the water we are taking, and there is temperature generation, delta T divided by time. So this is the temperature divided by time. According to the specific absorption rate, or the power dissipation divided by the mass of the magnetic nanoparticle will give the specific absorption rate, and that will decide how much temperature it is generated. We can measure the temperature in the colloidal suspension. So the major factor affecting the heat generation is size and shape of the magnetic nanoparticle, because the magnetic nanoparticle, the magnetic properties depend on its size as well as shape of the particles, as well as the susceptibility also depend on the size and shape of the particles, and the viscosity of the media and applied field parameters. So this is the hyperthermia instruments. So here we apply the magnetic field. So this is nothing but a solenoid. So this is nothing but a power. This is nothing but a power supply unit, and here there will be a solenoid, and according to the AC current you are applying, you are getting the current in the solenoid, and there will be the number of turns, and you can apply the field, and you can put your colloidal suspension in a vials, and you can see what is the heat generation through the computer monitor. So there will be temperature sensor probe, and we can get the heat. And with respect to time, at what applied field and what frequency, with respect to time, the heat, how much heat is generated, we can measure. And from the slope, delta T by delta T, this is temperature versus the time, we can measure the what is the ACR values. Fine. So to have the good colloidal stability, so to generate the colloidal stability, and for that good colloidal stability, we need the magnetic nanoparticles to be in a good suspension form. Am I audible?
Yes, sir. Yes.
Yeah.
Yes,
Yeah.
yes, you're
Yes,
right.
sir. We can hear you.
All right, all right. So if you see the iron oxide nanoparticles and surface functionalizations, so there are different functionalizations are there, and based on its size, shape, and surface properties, the physicochemical properties, especially magnetic properties, are which we are looking at, is getting changed. So we have the different functionalizations. There are amine functional, of course, many functionalizations are there. The amine functionalizations, carboxyl functionalizations. We have deuterionic or positive negative functionalization groups are there, and sometimes we have polymer functionalizations also. And because of the electrostatic stability mechanism or the static stability mechanism, we can control the colloidal stability of the nanomaterials. And that surface functionalization prevents colloidal aggregations. The nanoparticles should not aggregate, and it's control the final morphology. You can control the morphology of the nanomaterials by using the different functionalization techniques, and convert the surface hydrophilic surfactant is required to disperse the material in the hydrophilic solvent. So sometimes the hydrophobic surfactants are used, and that has to be changed to the surface ligand has to change through the certain techniques like ADC and HS techniques to get the hydrophilic functionalizations, and it also changes the surface charge of the nanomaterials. So to optimize the better colloidal stability, we need to functionalize with the different type of materials, different type of organic molecules. So based on this, this is our research work. Different functionalized Fe3O4 nanoparticles by co-precipitation methods. I cannot discuss all the methods, but I try to summarize in some of the major part of our research which we have carried out. So this is the one of co-precipitation method is one of the good techniques to prepare the nanomaterials. So in the co-precipitation method, you have to use the solvent like water, or sometimes you can use ethanol or water ethanol mixtures, and you can use a certain reducing agent like ammonia, ammonium hydroxide, or sodium hydroxides, or any acetate like sodium acetate. And you can the material has to be synthesized with a particular nitrogen atmosphere to control the proper oxidation and to form the iron oxide nanomaterials. So we have used the chloride salts over here, iron FeCl3 for 3 plus ions. As all most of you, as you are aware that the iron oxide have the plus 3 and plus 2 charges in the structure. So it is a inverse Pinel structure, so we must have to use the plus 3 as well as plus 2 in the proper stoichiometry ratio. And we did in a nitrogen atmosphere, and we coated with the glutamic acid. Here is the structure of the glutamic acid. There is hydroxide molecules are there over here. There is amine molecules are there over here. Then there is citric acid. We have taken the trisodium citrate. So three carboxyl groups are there. which can link either with the iron oxide, so iron ions in the nanomaterials by either electrostatic force or by covalent bonds or by coordination bonds. And then we have polyethylene glycol, and it's generally provide the steric stabilization. Then there is polyvinyl pyrrolidine, then ethylene diamine is there, diamine functionalization is there, and there is CTEP functionalization. In the CTEP we have methyl group is also there, and here a nitrogen plus group is there. All right. So then finally we did for the hyperthermia, the time versus temperature raise versus time. So let's see how these methods look like and how they are affecting the hyperthermia behavior. So these are the XRD patterns, and of course the XRD patterns according to the different planes, diffraction brackets, diffraction planes at particular 2 theta values, we can predict that this is the inverse pinel structure. No other impurities are there. And here we have this is the FTR spectra. I'll not go into one by one, but rather I can summarize in a particular way that generally iron metal oxide bonds are generally obtained below around 600 centimeter inverse, the band vibrations. So FUO band vibration is around 540 centimeter inverse. We have if there is ethylene glycol functionalizations, or the functionalization where OH molecules are there, we can get the water at 3436 around 3500. And if there will be some carboxyl group or some carboxyl groups are there, then C double bond O can be achieved at 1635. And these are, you have NS, then the NS bending or NS stretching vibration. NS bending is around 1627, and CS stretching vibrations are observed at around 2048 and 2918 centimeter inverse. So for from this, this is FTIR is one of the techniques to predict that there is the surface functionalization. However, this is not only the techniques to find the surface functionalization. However, you can we can go for the weight loss mechanism. Means in the nanoparticles, how in the surface it is coordinating with the ligands. So that will the TGA or thermogravimetry analysis give you certain informations, and you can see that there is the sequential heat loss when we increase the temperatures. And almost all the organic molecules, most of the organic molecules which we have used are burned around 350 degrees centigrades, and there is around the 5 to 10%. Sometimes it is 5 to 10% weight loss are there, and this is due to the surface functionalization of the nanomaterials. And zeta potential, which is the electric double layer, which is formation is there in the colloidal suspensions because of the surface functionalizations. We can get the zeta potential, and you can get glutamic acid, citric acid, polyethylene glycol, polyvinyl pyrrolidine, ethylene diamine. Here we are getting the negative zeta potentials because of the negative surface charge, but because of the N plus group, we are getting this in the CTEP, we are getting the positive surface charge. Fine. So this confirms the functionalizations, and this confirms the X-ray pattern, confirms the formations of the iron oxides. For more confirmations of the formation of the iron oxide, the presence of Fe2 plus and Fe3 plus ions can also be confirmed through the XPS, X-ray photon spectroscopy. Okay, so the nanometers looks like this. Of course, these are in different scales. As this figure has been taken in the different times, so the scale bar are different. So the size of the nanomaterials are generally below 30 nanometers. So all the nanomaterials are around below 20-30 nanometers. So I have given a precise size that you will see the size of the glutamic acid. So this is glutamic acid on. So it's 8 nanometers. This is citric acid is 10 nanometers. Then it is 9.93. This is the average size with, of course, a standard deviation. So all the nanoparticles are around 10 nanometers. I'm sorry, this is around 10 nanometers. So the during the co-precipitation techniques, of course, there is certain variation is there, plus minus 2-3 nanometers. However, all are almost monodisperse, and the nanoparticles formation is getting conformed. All right, as I told that there is the formation of the iron oxide. We have evaluated the presence of iron 2 plus and iron 3 plus from the XPS spectra, and it gives iron 2 p3 by 2 and iron 2 p half. We can estimate the presence of ions in the iron oxide. Of course, there is carbon and oxygens are also there due to the functional additions. All right, so let's go into the magnetic properties of the materials. and if you see the magnetic properties of the materials, it shows the superparamagnetic nature, as the size of the particles is around 10 nanometers. So it is well below the superparamagnetic critical diameter of the particles. And the saturation magnetization is quite high. It's above 60 in almost all the cases. I have given the data in the table. And of course, saturation magnetization is a intrinsic properties of the materials, and it is 92 EMU per gram for this I have given in EMU per gram unit. EMU is electromagnetic unit. So as it is an intrinsic properties, it should not change with respect to the size of the material. However, as the when it comes to the 10-20 nanometer, the surface effect plays a major role, and we have the surfactant also over here. So the movement of or the orientation of the movements on the surface of the nanomaterials are being not as that like the bulk, due to the difference in the exchange force. Fine. So we are getting the higher saturation still, which is good enough. The saturation magnetization is good enough, and this is the empty curve, the magnetization versus temperature, that whether it is super paramagnetic at room temperature or not. So it's around 300 Kelvin, almost is super paramagnetic. Slight coercivity is there, which is very negligible, and this slight coercivity may be due to the some particles may be the bigger particles, or very small coercivity, and it is less than 100 oersted, which could be neglected. And if you see the susceptibility versus the applied field, this is the susceptibility, and the susceptibility is maximum at 300 Kelvin. Initial susceptibility is quite high. If you take the M by H, the initial susceptibility is quite high, and saturation is also substantial, which is very good for the hyperthermia behavior, as I mentioned in the equations. So similar behavior has been found in the other coatings too. And this is the magnetic image curve for the bare nanomaterials without coating. Without coating, of course, there is the agglomeration, but still the magnetization is very high, because the surface coating, which we have around 5 to 7% or 5 to 10%, less than 10% coatings are there, and that coating layers like glutamic acid or citric acids, those are magnetic dead layers. So these are diamagnetic materials. This will not the materials will not contribute to the magnetization of the iron oxides, and hence it always possesses the lower than the bare one without coating. So these are the case. You can see that the saturation magnetizations are above 60 in every cases. This is the glutamic acid, this is citric acid, this is PZ, PVP, and EDA and CTAP. And this is the magnetic moment. We have calculated the magnetic moment per molecule of iron oxides. And the magnetic moments is coming around the theoretical values, around 2.76, 2.7 Bohr magnetron. And these are the blocking temperature. The blocking temperatures are well below the room temperature, and hence it could be utilized for the hyperthermia. And these are the anisotropy. As I told, that we have calculated the effective anisotropy, and the effective anisotropy depends on the structure of the materials. Even if it is iron oxide and the same molecules are there, However, the how the dipoles are getting arranged, or what is the exchange force between the different ions, we can say the different dipole moments, and according to that the exchange anisotropy or the anisotropy decides the factors, and you can see that glutamic acid possesses the higher anisotropy as compared to that. So as we know that anisotropy is one of the major role, and as well as the susceptibility, can it generate the higher heat than the other materials? We can check. So you will see that the magnetic susceptibility is also higher than the other materials. So if we'll see, then it possesses the higher uh, magnetic susceptibility as well as the higher anisotropic energy. Yeah. So if we will see that the glutamic acid one, of course, you can see the leading one is the glutamic acid, which possesses the higher temperature. It generates the higher temperature at very low time. Within 2 to 3 minutes, we can get. Of course, it depends on the concentrations too, because it depends on the mass of the solutions and mass of the magnetic nanoparticles. So there are the heat generation mechanism is depend on the mass of the how much magnetic nanoparticles we are using. So if you see that this is 1 mg per ml, this is 2 mg per ml, this is 3 mg per ml, and this is the field which we have generated, 35.8 kilo amps per meter. This is the H, and this is the frequency at which we are conducting the hyperthermia behavior, the frequency of the applied field. And we can see that around 45 degree can be generated in around less than 5-6 minutes in all the materials, not all the materials, but according to the magnetic parameters, the magnetic heat generations are there. It's less than around 10 minutes you can generate it. But if the suitable magnetic parameters are there, the heat can be generated less than 5 minutes too. So we can get around 5 minutes. The temperature is around 45 degree. So based on the type of coating, the even if it looks spherical, there is difference in the size, different in the magnetic and isotropy, and hence the relaxations are also different. So even if it looks similar, but due to the different surface functionalization and difference in size and the arrangement of the atoms inside the materials, the relaxations, this is the effective relaxation, this is the Brownian, and this is the tau n. So nil relaxations. So these relaxation mechanisms are different, as well as the susceptibility. So we have to measure the susceptibility as the hypothermic temperature also. So we can see that there is variation in the susceptibility, as well as there is variation in the effective relaxation of the materials. So according to the relaxations and the susceptibility, we are getting the higher ACR in case of glutamic acid in all concentrations. So actually, if you apply the field, if you increase the concentration, it doesn't mean that always the ACR will increase or the temperature will increase. See here, if we will increase the concentration over here, the at 3 mg per ml, where there may be coagulations and there may be settlement of the particles because of the interactions when we apply the field, and hence the magnetic hyperthermia is getting decreased. So for this is our comparisons. So the glutamic acid coated possesses very good properties as compared to the other one. So this depend not only the shape, size, but also its susceptibility, its magnetizations, as well as the effective anisotropy. All right. So for the same the glutamic acid, if we increase the again concentration, it shows that there is heating situation ability is there with respect to the concentration, and if you increase the concentration more than 3 mg, then it's the ACR value is getting decreased to 42 watt per gram. So this is power dissipated per mass of the particles. At the same applied frequency and same field strength, we're getting the decrease in the SAR values, and hence it depends on the concentrations too. So in summary, heating curve depends on the functionalization, shutter relaxation time, enhanced anisotropy, maximum magnetic susceptibility cause for maximum heat dissipation within short period of time. SAR is also concentration dependent, and heat dissipated in different surface grafted nanoparticle is found to depend on the magnetic susceptibility, magnetic anisotropy, magnetic relaxation time, as well as particle concentration. So all these parameter has to be optimized for to get the better behavior of the nanomaterials. So apart from that, we have prepared the different size shape of the nanomaterials, spherical, some ellipsoid kind of thing. This is the truncated octahedrons, nanorods, cubes, and it has been found that different because of different situations and different anisotropic constant, the SAR value also having the different values. How much time I have? Muhammad, Professor Muhammad.
Yeah, you have more time, no problem, sir. You have another
All right, all
maybe
right.
5 to 7 minutes. Yeah, because we started a little late, so you have some time.
Okay. All right, all right. Yeah. Thank you very much. Thank you very much. So apart from there, we have prepared the different type of nanomaterials which have the different type of specific properties. Some of the are iron platinum nanoparticles, which is very useful for biomedical application, and exactly it looks like this. Then we have prepared the core cell nanomaterials of iron platinum on the iron oxide. Then we have prepared these nano assemblies. Then we have prepared the iron oxide with the silica core. So this can be used for the different type of drug loading properties. With these are also with specific functionalizations. Then sometimes some optical imaging are being used with the or MRI. Gadolinium is the MRI materials which gives the T1 contrast agent, and iron oxide gives the T2 contrast agent. And we have also investigated uh, in the past with iron oxide composite with gadolinium phosphate. So these are some of the papers we have published on these materials. So I'll tell about as it's biomedical application, I'll little bit toss on the biomedical applications. So as iron platinum, as I told that it is one of the good materials which people have predicted that iron platinum releases iron and platinum, and iron generally when it goes to the cells, it oxidize, it decompose the hydrogen peroxide in the mitochondria and provide the reactive oxygen species, and this oxidize the material, and there is final cancers, death of the cancers. So these are some of the results on this has been taken from this paper, and the iron platinum releases iron more than the iron oxides. And in some paper, it has been found that the platinum specifically bind to the DNA of the cancer cells, and it changes the sequence. So as we work on the iron platinum, one of the disadvantages, it possesses very low magnetizations. So if you see the magnetization is 3.5 EMU per gram, which is not useful for the power dissipation. It cannot generate the heat. So why it cannot be combined with the iron oxides? We have checked that in iron oxide the magnetization is quite high. So if we make some composite of iron platinum and iron oxides, this can be combined for the combinational therapy. And we have tried some hydrothermal methods using the H2PTCl6 hydrochlorothalonic acids and iron chloride, and you can see that it will synthesize as 200 degrees centigrade, and you can see that from the XRD pattern there is clear iron oxide and platinum, iron platinums are there, and it forms the nanomaterial like this. So this form in cell assembly techniques. So small particles can aggregate and it forms the cell assembly, and it has been coated with the PEG diacid, the polyethylene glycol and carboxylic group are there. So one carboxylic group attached to the iron, and another carboxyl group is free, followed by the PEG. So it gives very good colloidal stability. And the size is around 100 nanometers. Sorry, the size is around 60 or 70 nanometers, and it is porous also, and hence it is very good for the carboxyl group, is very good for the attachment of the other drug molecules like drugs. Drugs has the some amine group which can be attached electrostatically with this particular material, and we have tested this. So if the formation of iron, platinum, and iron oxide, so this is iron and this is platinum. We have taken the line scan in STM image, and it has been found that the iron and platinum are distributed throughout this material. And this is quite porous, and this is the porosity measurement. And the porosity measurement says there is a mesoporous, and there is interpore are around 25 nanometer, and intrapore possesses 3.5 nanometers. And then if you see the zeta potential is also at normal pH. It is as negative groups are there, it is more than it is around minus 30, more than minus 30, and hence there is this is the attachment like this. So one carboxyl group is attached to the iron, another carboxyl group is free, which can be attached to the drug molecules very easily. And this, as it contains both iron, platinum, and iron oxide, the magnetization is also quite high. Of course, in the previous case I've shown that it is above 60, but here it is little bit 60, less than 60. And the presence of iron oxide is also confirmed from the some Vellore transitions. This is some transition due to the presence of iron oxides. And this is the colloidal suspension of the materials, and if you put the magnet, it can get separated, and when you remove the magnet, again it will come back to the colloidal form. And it has been found that when concentration dependent, C and A means composite nano assemblies. So this is iron, platinum, and oxide composite nano assemblies. And we can see that the water, only pure water doesn't generate any heat. If you see the bare iron oxide, it generates heat in around 4 minutes, 4 to 5 minutes. But in our cases, if you increase the concentration, you can generate the heat in a controlled way. But around 15 minutes, you can generate the heat with the concentration of 2 mg per ml, the 45 to 40, 44 to 45 degrees centigrade. All right. Then we have gone through the cytotoxicity of the material. And the cytotoxicity of the material, if you see the L929, this is the normal cells, and HeLa cell is the cancer cell, and it shows some cytotoxic effect in the cancer cell. However, it is quite biocompatible to the normal cells. So normal cells doesn't see any changes in the cells morphology after treating with the nanomaterials. However, we can get some cytotoxic effect in the HeLa cell, maybe due to the as I mentioned, the reactive oxygen species may be one of the reason. We have tested that one. Then we loaded with the drugs, drug molecules, that is doxorubicin, and the entrapment efficiency or loading efficiency is found to be around 80% is observed when 50 microgram of dox is incubated with 10 mg of nanomaterials in 1 ml of water. And you can see that this material is also showing some pH responsive release. And as blood, even if there is release is there at 7.4, which is the blood pH, this is one of the disadvantages, but still this has not yet been rectified by the several studies. It releases drugs, drug molecules in normal pH also. But in lower pH, with the cancer cell environment has the pH of around 4.3, so it releases higher amount of drugs. And when you apply the ACMF, the drugs release could be triggered to around 100%. So initially the drugs release at pH 4.3 is 60%, but when you apply the field with the applied magnetic field, the drugs release could be triggered. So if you see the cell biology, this is the control, only the HeLa cells, this is the control one. When it treated with the nanomaterials only, it's showing some around 15 to 10 to 15% decrease. Only pure dogs can be treated, then of course there is the direct cell deaths are there. But when you apply the ACMF, means AC magnetic field, only in nanomaterials, then there is around 40% cell deaths are there. But when dogs has been used, With the nanomaterials, the cell death is less than 50%, more than 50%. And when you apply the field with the hyperthermia and dogs, the cell death could be more than 90%. Then this is the image of the cancer cell with the dogs. Of course, this is the HeLa cell, and with the dogs, it's getting killed all of a sudden. But with the dogs and the composite assemblies, the nanomaterials loaded with the dogs, you can see that the fragmentations are there, sequential apoptosis or control apoptosis is there in the cells, and the cell death can be triggered with the application of the magnetic field. Then as we have tried in the hydrogen peroxide, we gave manually to hydrogen peroxide around 10 microliter of hydrogen peroxide, and we did the same the treatment with respect to the with dogs and magnetic nanomaterials and hydrogen peroxide, and the cell death is triggered. This is nothing but the ICP-AES, where the dissolution of the nanomaterials. So iron concentration at lower pH is very high. So it is releasing higher iron amount than the at 7.4 pH. So it has been found that, see here, this is the control one. As I told, the hydrogen peroxide, which is there in the mitochondria, and it decomposes in the presence of iron, and it produces the hydroxyl or hydroperoxyl radicals. We manually have given, or we included 10 microliter of hydrogen peroxides to induce the reactive oxygen species. And it has been found that when the dogs along with the nanomaterials and H2O2 has been given, the cell death is, there is complete cell death, and this is controlled cell death was there. So this is one of the synergistic therapy, where the nanomaterials functionalize with several biomolecules attached with the DOX molecules or drug, can be triggered through the hydrogen peroxide and application of the magnetic field. So this is all about what I wanted to present, and these are some related publications. These are some recent publications in scientific report: ACS Omega, some colloidal and interface A, colloid and surface A, Material Research Express, Journal of Superconductivity and Noble Magnetization, Journal of Nanoscience and Technology. These are some few years back we have published. So I just want to show some simulated simultaneous schematic how the dogs can be administered, or nanomaterials. So these are the nanomaterials when injected in the body. This is the tumors, and when you apply the field, then only it get accumulated. So we apply the field, it get accumulated in the cancer cells. And other targeting options are also there. This is magnetic targeting, but direct injection to the tumor site can also be administered, or coating with the specific antibodies also can bind to the tumor cell specifically. Then you apply the AC field, and you can trigger the release of the drugs molecules. As we have seen in ACMF, the release is higher, as well as it is pH sensitive release, and then we can treat the cancer cell. But there are a long way to go, because there are many limitations of these techniques are there, and that there is some clinical trial is also was there in Berlin in 2016, and the researchers got some great success out of that, but still some major issues has to be addressed before the use of these nanomaterials, because it creates a lot of inconveniences. That's all, and I want to acknowledge my funding agencies. This is my DST from Government of India, VIT University, Indian Council of Medical Research, Council of Scientific and Industrial Research, and of course I want to thank my research students and collaborators. These are my research students, and especially I want to thank for collaboration in the present situation and in the future, Professor Bruno, Dr. Nirmala Grace, the Director of Center of Nanotechnology Research, Dr. Satyanarayan, he's from Center CNR, and Dr. B. Oloska, he's from Poland, Police Academy of Science. Dr. Ragumani, he's from Baba Atomic Research Center, India, and Dr. Nana Sahib Thorat from Oxford, UK. Thank you for listening.
Thank you. Thank you very much, Professor. Definitely appreciate your contribution to the seminar. And it's definitely exciting to hear about these kinds of technologies that can revolutionize how we treat cancer in the future. So thank you very much.
Thank you very much. Yeah, I would be happy to answer if there is any questions.
Yes, now it's open for questions. Please feel free to unmute yourself and ask the question, or feel free to type it in the chat.
Niroj, there is Nirmala here.
Yes,
it was indeed a great presentation. Niroj, can you correlate, the functionalization with respect to the hyperthermia? I mean, functionalization of nanoparticles.
Yeah.
Is there any effect of that?
Yes. Thank you. It's a very good question. As I mentioned that the functionalization, which is the functional molecules, are not contributing magnetically. So this is called the magnetically dead layers. So when we increase the more functionalization, the magnetization are getting decreased. And according to the functionalizations, what we are getting is we are getting even if we are getting the same size, but this structure inside the atomic arrangements are different. And because of that, the saturation magnetization as well as the ordering of the magnetic dipoles are different. So when we apply the field, the susceptibility are different, means how they are getting aligned. And we know that during the power dissipations, it extensively depends on that anisotropy factor, the saturation magnetization, the susceptibility, and which is extensively controlled by the functionalization molecules or functionalized molecules. And because of that, it's giving the different hyperthermic behavior. Yeah.
Thank you, Niroj. And anything related to the shape? Yes.
Yeah,
anything related to the morphology?
Shape is greatly contributing to the anisotropy constant, because the effective anisotropy, what I told, then one is depending on the crystal structures, and another is depending on the shape of the molecules. So the effective anisotropy is contribution of the shape of the molecules and the crystal structure. And the crystal structure, when I say, is that suppose when you are preparing a nanomaterials, how the ions are oriented in different planes. Suppose people are preparing the different facets molecules, right? So whether it is more facets molecules are there in 1,1 plane or 1,100 plane or 110 plane, and according to that, the anisotropy is hugely extensively being contributed by the same anisotropy. Yeah.
Okay. Yeah. Thank you, Niroj.
Sir, this is Dr. Keyur Joshi. I had a question that, how do you apply controlled magnetism in the cancer cells to aggregate this nanoparticle in the cancer cell? You need to create a magnet there. So how externally do you apply magnetic field such that the magnetic intensity is highest at the cancer site?
Yeah.
Am I correct in
So
my thinking?
If it is magnetic targeting is not that as great technique as the antibody targeting. So if you have the antibodies, specific antibodies, then it can goes to the particular cancer cell easily. However, if we know the position of the tumor, if it is sitting outside of the body, in the surface of the body, then it can be easily controlled. But if it is deep seated, it's some liver or inside the body, then deep seated cancer, it is really difficult and really challenging. Like we are giving the MRI is around 7 Tesla, 9 Tesla fields are being applied. So the thing is that first the best technique is to functionalize with the antibodies so that it can go and sit in the tumor. Then we can provide the whole body whole body, we can provide the magnetic field in the whole body also. It's not a problem, because in MRI we are providing 7 to 9 Tesla, 7 Tesla, sometimes higher magnetic field, 4-5 Tesla are also there. But first thing is that attachment of the nanomaterial in a particular area should be very important, and magnetic targeting is not as that great as the targeting by the antibodies, functionalization with the antibodies. So did I answer, sir?
So the
Is it okay?
so let me understand this properly. So these nanoparticles get I mean they are part of the antibody, right? The drug that
No, sometimes we have the surface functionalization with the biomolecules that has to be tagged to the antibody. So the antibody will express, can go to the body cells, and it can attach to the specific portion where the receptor it will find. So antibody receptor interaction should be there. So cancer cell have different receptors. Different cells have different receptors. So those receptors has to be the locking mechanism is there. So if you put the antibodies,
once that locking takes
it will
place,
go and attach to the.
So once that locking takes place, you activate the magnetic field. Am I correct?
Yes.
Okay.
Yeah.
All right. Thank you, sir. It
So
was very interesting presentation, and it was very. I would say it was exhaustive. It's a lot of work. Thank you, sir.
Thank you very much, sir.
Thank you for your feedback.
Yeah.
Any other questions?
Yes, sir. Please.
Yes, please.
I have actually 3 questions, if I can ask them. So, Dr. Sahu, very good presentation, very informative, and thank you for a very detailed one. My first question is about the role of hyperthermia. Is that meant to be more of a catalyst, or rather, is that meant to help deliver the drug, or is it ultimately meant to remove an additional treatment like chemotherapy or high energy radiation therapy?
Yeah. So shall I reply, sir? Yeah.
Yes. That's the first question, and then I'll come to the second.
See, we want more convenient and more easy techniques for the treatment of the cancer, right? So basically, the chemotherapy and the radiation therapy has a lot of limitations. So because if you see the chemotherapy, after certain doses of chemo, it's contaminating all the body cells. So it has its own limitations, severe limitations, and radiation therapy also has the severe limitations because it is killing the normal cell. So without damaging the normal cells, if we can do in a controlled way, and if it is non-invasive, then it would be much better. So we are thinking about some good perspective for the cancer treatment. Yeah.
Okay, yeah, thank you. The second question that I had was, you mentioned hyperthermia capable of generating heat up to 45 degrees Celsius. I wanted to know over what area or volume that is localized. I know that there might be a temperature gradient in the area where we have the nanoparticles. So over what area or volume is that temperature localized, and will that actually help to target the cells?
Yeah, true. So generally, we have not yet studied that type of things, but there are results in vivo treatments are there, and few millimeter of the tumor size could be reduced in a mouse model. So it can be up to few millimeter. It can be up to few millimeter, and that also depend on the where the cancer is sitting, whether it is deep-seated cancer or it is sitting just in the surface or near to the surface. That is also a matter of concern.
Okay.
Yeah.
Thank you.
And that can be also triggered through the application of the different field, different strength of the field. So more the strength, more will be the activations.
Activation. Okay. And the third question that I have is around the area of hyperthermia itself. Hyperthermia is basically generating heat. Is there a way to dissipate heat or as in induce hypothermia by using nanoparticles, or is that a completely different topic?
As these are nanomaterials and it is in very small quantity, and generally it is to generate the heat in a controlled way. As I told that there are other techniques are also there, like for example photothermal therapy. So there are people are using some gold nanomaterials. So because of that plasmonic dissipation, if you apply some NIR laser, then it dissipates the heat. But that heat dissipation is very high. So 100 degree all of a sudden you will get. So those things is very dangerous. So controlled way of heating is very necessary for the control therapy. Yeah.
Wonderful. Thank you again, Dr. Sahu, for your presentation and answering my questions.
Thank you. Thank you very much for all the questions. Any other questions from our colleagues in India or here in the US?
Maybe Bruno is asking something.
Yes, Bruno.
Okay, so that Niroj, I had the impression that all these properties are strongly dependent on the surface of the nanoparticle, because also when you change the shape of the nanoparticle, you change completely the properties, the magnetic properties, the anisotropy, etc., etc. So, well, what is going to happen, according to your opinion, if you scale down more the size of the nanoparticle, if you go, for example, to a cluster size? What about all the properties, the magnetic properties?
Yeah, as I showed that according to the size of the crystal or size of the particles, the coercivity of the material, how it is depending on. So when we have a big particles, then generally we have multi-domain particles are there. Yeah, multi-domains are there.
Smaller size, not larger, smaller size.
Smaller in the single domain you are telling, right?
Yes. I mean, instead of having a nanoparticle, that means more a cluster of atoms in a way that you cannot find inside, or we can say inside the nanoparticle, anything that is like a bulk phase. Then you are scaling down really, and you have clusters. In clusters, of course, then the number of surface atoms with respect to the total number of atoms is even larger.
True, yeah.
So then what about all these magnetic properties? Can you comment?
So the thing is that if you create, I'm sorry. So if you create more surface atoms, generally the magnetic properties, it decreases. Magnetic properties means the saturation magnetization is getting decreased, because if you see the surface atoms with the bulk atom, there will be some magnetic exchange interactions are there, and it depends on the orientation of the dipole created in the nanomaterials. And that exchange interaction is quantum mechanical exchange interactions, and it is due to the the total angular momentum of individual magnetic dipoles. So as we are creating more number of surfaces, the exchange interaction will be decreased, because we are not creating more surface disorder and more spin disorderness will be observed, and hence the magnetic properties are getting decreased.
Okay.
Especially, yeah.
Okay, thanks.
And that surface, that is called, people are giving the term as surface canting behavior. Surface canting means surface spin canting. So this spin are not getting not proper ordered with the bulk, rather it is canted in the surface, and which cannot contribute much towards the magnetizations, because thermal energy is also there to destabilize this the ordering. Yeah.
Okay. Thanks.
Of course, we can discuss
Great,
more
thank you.
about it. Yeah.
Great. Dr. Niroj, thank you again very much on behalf of Binghamton University and VIT for joining us today to tell us more about your research. We're definitely glad to have you and appreciate your contribution. And it's good to hear a lot of interactions and interest in your presentation and your research. So thank you again for joining us today.
Thank you, Professor Mohammed. And I especially thank to Dr. Nirmala Grace for and Director Center for Nanotechnology, and Dr. Vasudevan, the Dean of SMAC, for giving this opportunity to to share my work in this joint conference webinar series. Thank you very much. Yeah.
Thank you, Niroj.
Thank you. Thank you. And before we conclude, I just want to let everyone know that again, as a reminder, that this is our last seminar in 2020, and we're looking forward to re-engaging with VIT on this seminar series starting January 14th, that's Thursday. And our first presentation will be on electrospinning biomimetic scaffolds for tissue engineering. This will be presented by Dr. Yenge Zhao, who's an assistant professor in my department, System Science and Industrial Engineering. And I will be sending a follow-up that will include Dr. Niroj's seminar and the recording, and also the abstract for this presentation. Please feel free to invite your colleagues, friends, scholars, and students to join us. And again, before we conclude the session, I'd like to thank everyone for joining us for 11 seminars so far. It was definitely great to see everyone and to see the level of interest from everyone around the globe. And thank you to Bruno again for joining us all the way from Italy. We are always glad to have your contribution. And on behalf of Binghamton University and VIT, I'd like to wish everyone a very happy and healthy and enjoyable holiday season, and a very productive and prosperous new year, and look forward to seeing everyone on January 14th. Thank you again, everyone.
Thank you, Professor Mohammed.
Thank you.
Happy New Year. Happy holidays.
Thank you. Thank you. Thank you very much.
Happy holidays. Yeah.
Thank you.
Yeah.
Thank you, everyone.
Happy holidays.
Okay.
Thank you.
Thank you. Bye-bye.
Bye-bye.